When most people hear the word electricity, a picture instantly forms in their mind. Tiny particles, electrons rushing through a wire like water through a pipe. Faster flow, more power. Slower flow, less power. It feels intuitive, comfortable, and completely wrong in the most important way. Richard Feynman loved pointing out mistakes like this, not to make people feel foolish, but to free them from bad mental models. Because once a wrong picture settles in your mind, it quietly controls how deeply you can understand the world. Here's the uncomfortable truth. When you flip a light switch, the electrons inside the wire barely move at all. Their average drift speed is often slower than a snail. If electricity really worked like water flowing through a pipe, you'd be waiting minutes for the light to turn on. But it turns on instantly, not almost instantly. That alone should make you pause and ask, if the electrons aren't racing down the wire, then what exactly is happening? This is where Feynman would smile, because the mistake isn't in the math. It's in the picture we're carrying in our heads. Electricity isn't primarily about electrons traveling from the power plant to your light bulb. It's about something far more subtle and far more powerful, the electric field. When you close a switch, you're not launching electrons on a long journey. You're rearranging an invisible structure that already exists throughout the entire circuit. That rearrangement spreads outward at nearly the speed of light, and that is what delivers energy. Think of it less like water flowing and more like pushing a long stick. When you push one end, the other end moves almost immediately, even though the atoms in the stick barely shift from their positions. The force travels through the structure, not by transporting matter, but by transmitting a change. Electricity behaves in a similar way. The wire is already full of electrons, like a crowded room. When the electric field changes, everyone adjusts slightly, and the effect appears everywhere at once. This misunderstanding persists because our brains crave simple analogies. Water in pipes feels familiar. Fields and forces acting through space feel abstract, almost philosophical, but physics doesn't care about what feels intuitive. It only cares about what actually works. Feynman often warned that knowing the name of something or having a comforting analogy isn't the same as understanding it. You can repeat current flows through a wire your entire life and still have no real sense of how electricity functions. There's also a psychological layer here that's easy to miss. Once we accept a simple story, we stop asking deeper questions. The water pipe analogy gives us permission to stop thinking, and that's dangerous not just in physics, but in life. Bad explanations don't just fail to explain, they actively block curiosity. They convince us we already understand when we don't. The beauty of the electric field idea is that it forces humility. It reminds us that the most important parts of reality are often invisible. The energy that lights your home doesn't rush through copper like a river. It moves through the space around the wire, guided by it, shaped by it, but not confined inside it. That realization alone changes how you see power lines, circuits, and even the concept of connection itself. Feynman believed that real understanding feels slightly uncomfortable at first. It stretches you. It breaks a mental picture you were attached to and replaces it with something less cozy but far more accurate. And once that happens, you don't just know more, you see differently. Electricity stops being a mechanical process and becomes a story about fields, relationships, and invisible structures shaping the visible world. So the next time you flip a switch, don't imagine electrons sprinting down a wire. Imagine a quiet, nearly instant rearrangement of reality itself. Because the moment you let go of the wrong picture, you make room for a deeper truth, and that habit of questioning what feels obvious may be the most powerful current of all. Once you let go of idea that electricity is electrons racing through wires. A deeper and more interesting picture begins to appear. If the electrons aren't doing the heavy lifting, then what is? This is where Richard Feynman would gently shift the conversation away from the wire itself and toward the space around it. Because the real work of electricity doesn't happen inside the copper. It happens in the invisible architecture that surrounds it, the electric field. When you flip a switch, something remarkable occurs. The electric field throughout the entire circuit reorganizes itself almost instantly, spreading at nearly the speed of light. This field already exists everywhere along the wire and around it, even before anything is turned on. Closing the switch doesn't create the field from scratch. It changes its shape, and that change is what delivers energy to the bulb, the motor, or the screen in front of you. The wire's role is not to transport energy like a pipeline, but to guide and constrain the field, giving it a path to follow. This idea feels unsettling because we're not used to thinking of empty space as active. We instinctively trust solid objects. We believe in things we can hold, see, and touch. Fields, on the other hand, feel like mathematical ghosts useful for equations, maybe, but not real. Feynman rejected that instinct entirely. To him, the field wasn't a trick or a shortcut. It was the thing itself. The field carries energy, momentum, and information. Ignore it, and you miss the entire mechanism. Here's the part that quietly overturns everything you think you know about wires. Most of the energy in an electrical circuit travels outside the wire, not inside it. The wire simply marks where the field is allowed to go. The energy flows through the surrounding space, guided by the presence of the conductor, like a river shaped by its banks. This is not an interpretation or a metaphor. It falls straight out of Maxwell's equations. The math insists on it, even if our intuition resists. There's something philosophically unsettling about this. It means that the empty space around us is doing more work than the solid material we rely on. It suggests that structure matters more than substance. The wire isn't powerful because of what's inside it. It's powerful because of how it shapes relationships between forces in space. And that's a pattern you start seeing everywhere once you're alert to it. Systems where the connections matter more than the components. Feynman loved ideas like this because they expose how easily we confuse containers with causes. We look at the wire and assume the power must be inside it. But the wire is just a constraint, a boundary condition. The true action is in the field, silently filling space, responding instantly, and doing the work without ever being seen. The danger isn't that this is hard to understand, it's that we don't even realize we're misunderstanding it. Psychologically, this matters more than it seems. When we believe that power comes from obvious, visible sources, we overlook subtle influences. We underestimate systems that operate quietly in the background. The electric field teaches a humbling lesson. The most important forces are often the least noticeable. They don't announce themselves. They don't rush. They simply rearrange reality until outcomes change. This also explains why electricity behaves the way it does over long distances. Energy doesn't wait for electrons to migrate from one end of a wire to the other. The field adjusts everywhere at once, limited only by the speed of light. That's why your device responds immediately, and why electrical systems can remain stable across enormous networks. The coordination happens through fields, not through traffic. Feynman would often say that understanding nature isn't about memorizing facts. It's about learning what to pay attention to. And electricity trains your attention away from objects and toward relationships. It teaches you that reality isn't built from things alone, but from interactions spreading through space. So the next time you see a wire, don't think of it as a carrier of power. Think of it as a sculptor of invisible forces shaping a field that does the real work. Because when you start noticing the unseen structures guiding outcomes, you don't just understand electricity better, you begin to understand how change actually happens. Once you understand that, electric field is doing the real work. Another common confusion starts to unravel. People are taught to focus on current, the number of electrons moving through a wire each second, as if it were the star of the show. But current by itself explains almost nothing. Richard Feynman would point out that staring at current without understanding what drives it is like counting footsteps without asking who is doing the walking or why. The real question isn't how much is moving, but what is pushing. That push is voltage. Voltage is not energy flowing, and it's not something stored in a wire like fuel in a tank. It's a measure of difference, a tension in the electric field between 2 points. When you create a voltage, you create an imbalance, and nature responds by trying to smooth it out. Current is simply the system's response to that imbalance. No voltage, no current, and more importantly, no useful work. This distinction matters because it corrects a deeply ingrained mental habit. We tend to measure activity by motion. We trust what moves. Current feels active, voltage feels abstract, but electricity doesn't reward motion for its own sake. You can have enormous current flowing in a loop with almost no voltage and almost no energy transfer. On the other hand, you can have very high voltage with tiny current and still move vast amounts of power. Power, after all, is the product of both. Ignore voltage and you misunderstand the entire system. Feynman loved exposing this mistake because it reveals how easily we confuse cause and effect. Current is the effect, voltage is the cause. The electric field created by a voltage difference sets charges into motion, not the other way around. And yet, most people talk as if current is the driving force, as if electrons decide to move first and the field somehow follows. Physics doesn't work that way. The field comes first. This insight also explains why electricity can be dangerous in ways that seem counterintuitive. People often ask why high voltage lines can kill you even when the current might be small. The answer is that voltage determines how violently the electric field can rearrange charges in your body. Current is what flows once that rearrangement is possible. Voltage opens the door, current walks through it. Confuse the two and you misjudge risk. There's a philosophical lesson hiding here. We often obsess over visible outcomes while ignoring the conditions that make them possible. We measure success by output, by motion, by noise. But the real power lies in the differences that create pressure imbalances, that force systems to change. Voltage is invisible tension, and tension is what drives transformation. This is why power companies transmit electricity at extremely high voltages. They aren't chasing current, they're minimizing it. Higher voltage means the same power can be delivered with less current, reducing energy loss. It's an elegant solution that only makes sense once you abandon the idea that more current automatically means more power. Understanding voltage doesn't just clarify electricity. It reveals how intelligence often looks like restraint. Feynman would emphasize that learning physics is learning to stop telling comforting stories and start respecting precise ones. Voltage isn't a substance, it's a relationship. It exists only between points, not inside objects, and yet that relationship governs everything that follows. The electrons move because the field demands it, not because they want to. Psychologically, this reframes how we think about influence. The strongest forces aren't always loud or fast. Sometimes they are quiet differences, patiently shaping behavior until motion becomes inevitable. When you understand voltage, you start noticing how gradients of pressure, of temperature, of opportunity drive change everywhere, not just in circuits. So stop asking how much is flowing and start asking what is pushing. Because when you learn to see the invisible forces that create motion, you gain a deeper control over both machines and ideas, and that shift in perspective is where real power begins. When you step back and look at all of this together, the slow electrons, the invisible electric field, the quiet dominance of voltage, you begin to see that the real problem was never electricity itself. The real problem was the story we told ourselves about it. Richard Feynman believed that the greatest obstacle to understanding isn't ignorance, it's the illusion of understanding. Once you think you know how something works, you stop looking closely, and that's where misconceptions harden into permanent limits. The water in a pipe analogy is a perfect example. It's simple, memorable, and just accurate enough to survive without being challenged. But it quietly trains the mind to think in the wrong direction. Instead of asking how fields interact across space, we imagine particles marching down a line. Instead of seeing relationships, we see objects, and once that habit sets in, deeper insight becomes difficult, not because it's too complex, but because it contradicts something we already know. Feynman had very little patience for this kind of false clarity. He often said that science is about being comfortable with not knowing, about holding ideas loosely enough that reality can correct them. A bad explanation doesn't just fail to explain, it blocks better ones. It fills the space where curiosity should live. And electricity, perhaps more than any other everyday phenomenon, exposes how damaging that can be. What makes this especially important is that electricity is not a niche subject. It powers modern life. When our mental models of such a foundational system are wrong, we don't just misunderstand physics, we misunderstand how complex systems behave in general. We learn to expect simple causes, linear flows, and visible mechanisms, but reality is rarely so cooperative. It runs on fields, gradients, feedback loops, and invisible constraints. This is why Feynman insisted on understanding things from the ground up. Not memorizing formulas, not repeating analogies, but asking relentlessly, what is really doing the work? In electricity, the answer turns out to be the unseen structure of space itself, shaped by conductors and driven by differences. Once you accept that, the subject becomes clearer, not murkier. The confusion came from oversimplification, not complexity. There's also a deeper psychological cost to holding on to wrong models. When we rely on explanations that feel intuitive rather than accurate, we train ourselves to prefer comfort over truth. We become less willing to question our assumptions, less tolerant of ideas that feel strange at first. And that habit doesn't stay confined to physics. It spills into how we think about society, technology, and even ourselves. Feynman understood that learning how to think matters more than what you think. Electricity becomes a training ground for intellectual honesty. It forces you to admit that the obvious picture is often wrong, that the important action may be happening somewhere you're not looking. And once you've learned that lesson in one domain, it's hard not to apply it everywhere else. The irony is that abandoning the misconception doesn't make electricity harder. It makes it elegant. Suddenly everything fits. Instant responses make sense. Long distance power transmission makes sense. The role of voltage, the importance of fields, the slowness of electrons, all of it clicks into place. What felt confusing before now feels inevitable. This is the kind of understanding Feynman valued, not the ability to recite facts, but the ability to see clearly. He wasn't interested in making things sound profound. He was interested in making them true, and truth, when you really grasp it, has a way of changing how you think far beyond the topic at hand. So the real lesson here isn't just about electricity. It's about the courage to let go of explanations that feel good but fail under scrutiny. Because the moment you replace a comforting story with an honest one, you don't just learn something new. You expand the range of what you're capable of understanding.